Okay, so now we're going to be looking at covalent bonding for a little bit. So if we remember that all of our substances that we find in the universe can be split down into two general categories. We have simple substances, and simple substances are ones where we can fix the number of atoms. We can say, for example, water is a simple substance, and we can say a water molecule has only two hydrogens and one oxygen, and that's the limit of it. We can put a circle around that and say that is our water. Other ones are giant substances, whereby we can say a similar thing. We can say sodium chloride, for example, is a giant substance, but we can't say exactly how many sodiums or exactly how many chlorines there are in a particular piece of sodium chloride without counting them, but we do know that for every one sodium ion in there, we have one chloride ion. Giant substances can have any of the three major types of bonding. We can have covalent giant substances, ionic giant substances, or metallic giant substances, but simple substances are limited to only covalent bonding. And so therefore for these type of substances we call them simple covalent substances, and water is a classic example. Now these, if there wasn't any bonding between the molecules, if we had two molecules of water for example, and we say that's the extent of the molecule. If there was no attraction between these two, then there would be gas, and we would only have gases for our simple substances. But there must be some kind of force between these two, because we know that water can exist in a liquid state and also in a solid state, and we call these intermolecular forces. So inter meaning between, and molecular from molecules, and there's a force between them. And that's similar to what holds together our ionic substances. If we remember, we have sodium as a positive ion and chloride as a negative ion. This positive on the sodium and the chloride on the negative are attracted to each other, and that's what holds the whole substance together. So, looking at our covalent bonding, and we'll come back to intermolecular forces later. Looking at our covalent bonding, we need to define what we mean by this phrase first of all. So let's split that down. So if we look at this word, it's made up of two parts. We have co and we have valent. So co simply means together. For example, when you cooperate with someone, you work together with them. And valent is an indication of the outer electron shell. So the valence shell of an atom is its outer electron shell. It's the one on the outside, and it's the one involved in all bonding. So we call that the valence shell. So when we have two atoms together, which are putting their outer electron shells together, we call it a covalent bond. So just a reminder that our shells need to have a maximum of 2 electrons in, second shell 8, third shell 8, fourth shell 8. That is the model for GCSE science for now. If we can attain this full outer shell, then we have a stable compound. Covalent bonding is limited to when two nonmetals bond with each other. So if we remember our periodic table, we can generally split this down here with this zigzag line, and we generally say that this side of the periodic table is metals, and this side of the periodic table is the non-metals. So if you recall your ionic bonding, any metal and any non-metal will generally bond by ionic bonding, and if we have two non-metals together, then we need our covalent bonding, and in these circumstances we consider hydrogen to be a non-metal. So to remind ourselves how this bonding works, if we take lithium and fluorine as an example, our lithium would have 2 electrons in its first shell and 1 electron in its second shell, and fluorine would have 2 electrons in its first shell, let's use dots there, and group 7, so 7 electrons in its second shell. So because we have a metal and a non-metal here, and a non-metal, then generally our non-metal will gain an electron, our metal will lose an electron, so that electron gets transferred down there, and we end up with a lithium ion with its 2 electrons, and because it's lost a negative particle, it becomes positively charged. and our fluorine has gained electron, circles, sorry, 1, 2, 3, 4, 5, 6 and 7, and it's picked up that electron from fluorine, and so overall we now have a negative charge. So this positive lithium ion and negative fluoride ion are now attracted to each other by ionic bonding. This is different when we are talking about hydrogen and fluorine. So now I'm not going to draw my circles for my shells, because as you can see they're not being drawn very neatly here, and we're only interested in the outer shell here because of the phrase covalent, our valence shell or outer shell. So our hydrogen in this case has just got 1 electron in its outer shell. Our fluorine again has still got its 8 electrons. I'm going to draw them in green this time. 1, 2, 3, 4, 5, 6 and 7. And now we could take our hydrogen, its electron, and put it into our fluorine, but then this hydrogen here would have no electrons in its outer shell because it's the only shell. So what happens here is our hydrogen and our fluorine, they combine their outer shells and they share the electrons, and we indicate that here by putting the electrons between the two atoms which are sharing them. The remainder of the fluorine electrons, they're not shared with the hydrogen, they still remain exactly where they were before. So here they're associated with the fluorine, here with the fluorine, here with the fluorine, and over here these electrons remain with the fluorine. But this one here, which was on its own, this unpaired electron, and this unpaired electron, they end up pairing up, and we now have a covalent bond. If we want to check that we now have full outer shells, if we ignore fluorine for a second, look at this hydrogen, we now have 1 electron, 2 electrons associated with this hydrogen, so we now have a full outer shell for the hydrogen. If we were to draw it on just to indicate that. So this hydrogen now has 2 electrons in its outer shell, and if we look at the fluorine and its outer shell, which is now overlapped, we have 1, 2, 3, 4, 5, 6, 7, 8 electrons for fluorine, so we have a full outer shell. And we draw it with this line between it, and this line simply indicates the covalent bond, which is the sharing of 2 electrons. Okay, and we call this a single bond. Okay, so exactly the same process works for all covalent bonding. So if we move on to the next example, hydrogen, hydrogen, it's a relatively simple one. So hydrogen with 1 electron in the outer shell and another hydrogen with equally 1 electron in the outer shell. Put these two together and hydrogen simply shares the electron and we end up with H. Fluorine over here, 1, 2, 3, 4, 5, 6, 7 electrons. Let's do a different colour here. This fluorine, 1, 2, 3, 4, 5, 6 and 7. So here we have 1 unpaired electron, here we have 1 unpaired electron, so if we share those electrons, and then the unshared ones over here, and then our fluorine again, we are now sharing our electrons. So this fluorine now has a share of this electron and its original one, so 1, 2, 3, 4, 5, 6, 7, 8 electrons in its outer shell, and this fluorine 1, 2, 3, 4, 5, 6, 7, 8. So we have a fluorine molecule with a single covalent bond between it. Exactly the same argument can be made for 2 chlorines. So here we have chlorine still in group 7, so again this one will have 7 electrons in its outer shell, and this chlorine has 7 electrons in its outer shell. Put those two together and they share the electrons that's unpaired. 4, 6. So again, ignoring this chlorine here for a second, centering on this one, 1, 2, 3, 4, 5, 6, 7, 8 electrons. So this has got a full outer shell, and exactly the same here, so we can draw chlorine as a molecule. Now when we get on to slightly more complicated molecules, hydrogen here for example has one electron in its outer shell, this hydrogen has another electron in its outer shell, and this oxygen in group 6, so it's got 6 electrons in its outer shell. So this oxygen needs 2 more electrons to get the full out. This hydrogen just needs 1 electron to get its full outer shell, which only needs 2, and this hydrogen also only needs 1. So this all works out nicely. This oxygen can share these 2 unpaired electrons with the hydrogens. So this hydrogen here can share on this side, share its electron, and this hydrogen here can share on this side, and we end up with our water molecule, which we draw as HOH. If we want to go a little bit further, we could show these unshared electrons here, 1, 2, 3, 4, and then this would be our single covalent bond, and these ones here would be unshared electrons, so we call them the lone pair of electrons. Okay, because they're not being shared with anyone, so they're on their own. Okay, so that would be our water molecule, 2 single covalent bonds to make sure water's got its full outer shell. Moving on, if we have 3 hydrogens this time, one electron, and 1 electron. Nitrogen, looking on our periodic table, is in group 5, so it's got 5 electrons in its outer shell. So now we need 1 more, 2 more, 3 more electrons to fill up this nitrogen outer shell, and we happen to have 3 hydrogens here. So it stands to reason again that we share the individual electrons with each of those hydrogens, and we end up with our ammonia molecule, or NH, and this we call ammonia. And we have a unshared pair of electrons here, so 1 lone pair, and then hydrogen over here with carbon, our very first hydrocarbon, which you will recall from core science. Carbon group 4, so only 4 electrons in its outer shell, and again if you work through the logic, then we have pairing up of electrons here, and our methane molecule has 4 hydrogens to it, so we end up with methane just like so. Okay, because all of the electrons are being shared, we don't have any of these lone pairs, and this has very interesting effects on the solubility and the boiling point and melting point of this substance compared to ammonia, but we'll come back to that at a later date. So that's all the simple molecules you need to be able to know. You need to know hydrogen, fluorine, chlorine, water, ammonia and methane, and then slightly more complicated is if we have oxygen with its 6 electrons, 1, 2, 3, 4, 5, 6, and another oxygen over here with 6 electrons. This oxygen needs 2 more electrons to fill its outer shell, this oxygen needs 2 more electrons to fill its outer shell, and they have 2 unpaired electrons each, so if we put them together and share those 2 unpaired electrons, then our oxygens can fulfill their full outer shell. It's just they happen to be sharing 2 electrons with their neighbouring oxygen. So 4 in the middle, 2 there makes 8, and 4 in the middle, 2 there makes 8. This we draw as 2 lines now, and we call this a double covalent bond, because we have 2 pairs of electrons being shared. I'm just about out of time. Our carbon forms 2 sets of double bonds to form the carbon dioxide molecule, and I'll let you draw that for yourself.